Let's consider a solid E, meaning with everything inside, right? So this is not a hollow thing, the solid. And let's consider also the surface here. So the surface is going to be S. So the surface is something two-dimensional, the solid is something three-dimensional. So we consider the solid E that has as boundary the surface S. So then the divergence theorem, what it says is that the surface integral of the vector field can be also calculated as the triple integral of a solid whose boundary is the surface. And what we have to put in the integrand would be the divergence of the vector field. Remember that the divergence of a vector field is a scalar, is not a vector field. So this, in that way, this is a simple triple integrals that you know how to calculate. So the divergence theorem gives us an alternative to calculate the surface integral instead of directly by calculating a triple integral instead of the solid enclosed by the surface. Let's calculate this surface integral, the surface integral of this vector field where the surface is determined by this paraboloid, this cylinder, and the plane z equals 0. So we have this surface all around that encloses there a solid E. Okay, so we could calculate this surface integral by doing the flux of this over all these surfaces, right? Though it will be much easier to apply the divergence theorem and just calculate the triple integral over the solid. In order to do that, first we need to calculate the divergence. So remember that the divergence of a vector field is just the addition of the partial derivatives. So let's do the partial derivative respect to x is just y plus the derivative respect to y here is minus 2y over 2, so just minus y, and plus the derivative of z respect to z, which is just 1. And so this y minus y is 0, so it's 1. It's just a function that is constant, in this case, the divergence of this vector field. And so all what we need to calculate here is the triple integral over this solid of the function equal to 1. So this is the integral that we need to calculate to get the value of the surface integral. Considering the functions that determine the solid E, will be good to use here cylindrical coordinates. This is x equal r cosine, y equal r sine, and z equal z. And the differential we have to multiply by r. The integral from 0 to 1 dr. Since the radius here is going to vary from 0 to 1. So the angle, since the angle goes all the way around, is going to be the integral from 0 to 2 pi d theta. And the z is going to vary from 0 to this surface. From 0 to 4 minus, we take a minus 3 as a common factor there, will be minus 3 r squared and then we multiply the 1 by r, by this r. So this is the integral that we have to calculate now, integral between 0 and 1 of the integral between 0 and 2 pi, and let's calculate first this integral here. So the integral of this respect to z is going to be just r z, evaluate between 0 and 4 minus 3r squared. So this is the integral then, d theta dr. Okay, let's do the evaluation now. This is going to be the integral between 0 and 1 of the integral between 0 and 2 pi, and we're going to evaluate now z in this value. So that will be r times 4 minus 3r squared. So now we need to do the integration of this respect to the angle. Again, this is a constant, goes out, so it will be the same case that before. It will be just the same. Let me just multiply this, 4r minus 3r cubed. That goes out, is a constant, times the angle evaluated between 0 and 2 pi. So this is the integral between 0 and 1. Let's do the evaluation now. The evaluation will be at 2 pi and now the final integral we take will be the integral of that. We take 2 pi as a constant out and we integrate this respect to r. 4r squared over 2 minus 3r4 over 4. And this should be evaluated between 0 and 1. So let's evaluate at 1. So first 4 over 2 here is going to be just 2. Evaluated at 1 will be 2 minus 3, 4 minus 0. And so here will be 2 minus 3, 4 is 5 fourths. So the final answer is 5 pi over 2. So this is the value then of the surface integral without using any of the methods of calculation of the surface integral, but using the divergence theorem instead.